In a time where AI work is getting reduced to sending an HTTP request to an LLM, we are going to go back to the basics. Back to when training models was done on your CPU and using a neural network meant having to implement your own backpropagation. So the goal of this series is to implement a PyTorch inspired deep learning framework from scratch in C++ to gain more insights into how deep learning actually works. In the last video we implemented our own Tensor class, which is the building block of almost every deep learning framework. We added support to store scalar, one-dimensional and two-dimensional data in this tensor, and also added methods to add and multiply different tensors, which are the only two operations that are basically needed to do a forward pass in our neural network. So that's it for the quick recap, let's get started. As this will be the most challenging video so far, I even whipped up the old drawing board to create some handcrafted animations specifically for you. If you were instead looking for an actual professional mathematician with professional animations, explain them to you over some classical music while you can sip some tea in the background, well, there are a lot of channels where you can find that stuff, but here this is a computer science channel, so everything might be a little bit more rough around the edges, and we will learn just enough math so we can actually implement our neural network. So as you know, in our previous video we implemented the addition and multiplication operation. And basically all that a neural network is doing is just take an input and then just apply some of these operations on it. For example, first we are going to multiply it with a tensor, then we are going to add another tensor to this, then we take this output, we multiply it with another tensor, and take this output and add another weight to it. So this then will be the final output, which you can also say like this is the prediction. And what we now need to do, but we are skipping ahead for a while, but we basically want to know how close this output is to the real output. For example, in our case, in the neural network we are going to train, the input will be an MNIST image. So it will be, for example, an image, let me draw something of the number 7. And this output, for example, then might be saying it's 6, but of course that isn't correct. So in the loss function, we are measuring how close the output is, the actual output is to the output we are predicting. And you can basically consider this once again as an additional operation in an entire operation chain. So we can write this like this. We can say at the end we also have to check how close the output is to our real output, and then just consider this entire chain as all the operations that happen in a forward pass of our neural network. However, just passing inputs through a forward pass through our neural network, of course, isn't very useful. We actually want our neural network to get better over time. And this is done with this loss function, as the loss function measures how bad that the network is at predicting. So, of course, it increases if this number, for example, is far removed from the actual expected output. So what we basically need to know is how we can move all these tensors in a direction such that the loss function decreases. And if you've ever followed a calculus class, you know this has something to do with derivatives. And more concretely, what we want to know, for example, is how much what the derivative of the loss is with respect, for example, to this weight W1. And let's do a quick recap of derivatives anyways, because there might be some of you who are maybe a bit younger and haven't seen this explained, or you might want a quick refresh. So let's just plot the loss, and here to w1. You should just, for this example, consider w1 as a scalar, such that it can be plotted on a single axis, but in actuality this might actually be a 2D tensor. But anyways, the loss might look something like this, and our first version of our w1, let's call it w1 0, might be something around here. And as you can see, to make it that the loss decreases, we actually need to move the w1 all the way until we minimize the loss function. And how do we know if we either need to increase or decrease our w1? Well, that's being done with the derivative. And what the derivative basically does is it basically calculates this. It says like, what if we would increase the w1 by a very small number? So we just increase it with a small number. How much would then actually the loss move? So the formula is given by this. Okay. And we might, and then you then take the limit to be more precise of this e when it goes to 0, but that's just technical details. But you can already eyeball this and see if we would increase the w1 by a very small amount. You can see if we go up, we end up here on the graph, and you're basically subtracting a larger number from a smaller one. So the derivative at this point will be smaller than 0, so it's actually negative. And we now know that we have a negative derivative in this direction, and what we then basically do is take our initial weight, for example, okay, w1, and what we then do is we move in the direction opposite to the derivative, as if the derivative is negative, we need to increase the w1, but when the derivative is positive, for example here, we actually need to move back, so we need to move in the opposite direction of the derivative. So we are going to update the w1 with minus the derivative of L according to w1, and then we also multiply it with something called a learning rate, and this is a very small number such that we are actually not moving too fast, and this then will be our w11, and you basically repeat this process continually, updating w1 such that we eventually hopefully end up right here at the loss. But it can actually also happen that we overshoot it a bit and, for example, end up here, but then we see that the loss is positive, that the derivative to the loss is positive, which means we are actually going to decrease the w1, and eventually we end up right here. At least we hope so. So what we now need to find out is a way on how to calculate the derivative of the loss with respect to every tensor for which we want to adjust the numbers of in our neural network. And this formula is actually given by us with the chain rule of calculus, which explains how to calculate the derivative of composite functions. And I pasted some explanation right here. What we basically need to do is, if a variable z depends on a variable x indirectly, and instead the variable z depends on the variable y, and it's the variable y that depends on x, we just need to multiply the derivative of z with respect to y times the derivative of y with respect to x. A more intuitive explanation might be, let's say, a car doesn't directly depend on the speed of a walking man, but we, for example, know that a car travels twice as fast as a bicycle, and the bicycle is 4 times as fast as a walking man, then we know that the car travels 2 times 4 is 8 times as fast as the man. So we just need to multiply how much faster a car is than a bicycle with how much faster a bicycle is than a walking man. If you want to generalize it to multiple composite functions, then you basically see, let's say if we apply n functions on a given input, for example in this case the input is actually x, let me draw x instead of we had I as an input, but the input is here x, and we see that if we want to calculate the derivative of f1 with respect to x, and f1 doesn't directly depend on x, then we have to multiply this whole chain of derivatives until we eventually arrive at the function f1, for which we can actually calculate the derivative with respect to x. So let's make this all a bit more concrete and rewrite our running example into this functional format so we can apply the chain rule more visually. Let's say we defined the first function as f1, and this just is the input times w1. Then f2 just takes this f1 and adds b1, f3 which takes this f2 and multiplies with w2. Then we have f4 which takes this f3 and adds b2, and finally we arrive at our loss function, which just takes f4 and checks how close it is to the expected output. So we can basically then also write it as follows. Loss is basically just f4 applied onto f3, applied onto f2, applied onto f1, and input to f1 is just I. So let's now just apply the chain rule to calculate how much the derivative of the loss is with, for example, to w1. And we know that's only this f1 that actually depends on w1, and the rest depend on it indirectly. So we apply the chain rule and first need to calculate how much the derivative of the loss is with respect to f4. Then how much the derivative of f4 is with respect to f3. F3 with respect... This drawing is pretty hard, I think. But okay, with respect to f2 times the derivative of f2 with respect to f1. And then we finally have f1, and we can calculate the derivative of f1 with respect to w1. And thing you should also realize, I'm just going to make it a bit obvious, a bit more explicit I mean, but let's say I want to calculate the derivative of loss with respect to f1. This will be the same as above for the large part. We are just going to calculate it up until the f1. Okay, so this is basically the derivative of the loss with respect to f1, and you can see this is exactly the same as the first part of this equation. So what we can effectively also say is that the derivative of the loss with respect to w1 is just equal to the derivative of the loss with respect to f1 times the derivative of f1 with respect to w1. So what I actually want to indicate with this is that we only, to calculate the derivative of the loss with respect to a certain tensor, we only need to know two things, and that's the derivative of the loss with respect to the tensor that is the output of the operation that we apply onto w1 tensor, and then just the derivative of the operation we are going to apply with respect to the tensor that we want to know the derivative of with respect to the loss. This will become a bit clearer in a while, but yeah, that's why I did this derivation. Okay, let's now make our final, and I promise final, visualization, which will allow us to easily make the transition to C++. So let's define the operations of our, or of an example neural network in graph format, where we are defining tensors and then are just applying operations on tensors to eventually arrive at a loss value, which is just a scalar. And what we should first off realize is that at the end of our neural network, we will just have this loss tensor as outputs, but we then want to update the actually calculate the derivatives of the loss with respect to all the tensors of our neural network. So how do we do that? Well, we first off need to know which tensors were involved in eventually getting this loss value. And here you can easily see it in graph format, but we need some way in our C++ code, in our tensor class, to keep track of this entire graph. And the way we are going to do this is by introducing a parents member variable for each tensor. And this parents variable will just, for each tensor, keep track of which are the parents of that specific tensor. So for example, for the tensor f, it will contain pointers to C and D. And if we do this for all the tensors which eventually led up to the loss, we can just through the parents of the loss function reach these f and g, and then once again iterate to those parents and basically reach everything within the graph. The second thing we of course want to do is keep track of the gradient of the loss with respect to that specific tensor in that specific tensor, of course. So eventually we want the tensor A, we wanted to store the derivative of L to A in a member variable which we will call grad. Okay, and the third thing we should realize is if we, for example, want to calculate the derivative of L with respect to some parameter A, then we just need to calculate, as I explained before, in this case the derivative of L with respect to C, and then just the derivative of the operation that uses A. In this case it was A plus B with respect to A. And this just corresponds to what we derived here, which is the derivative of the loss with respect to some tensor is just the derivative of the loss with respect to the output of the operation in which the tensor was involved, and then just times the derivative of the operation itself in which the tensor was used with respect to the tensor. So that's just what we have written here. And let's for completeness also write the derivative of L with respect to B. This will once again use the same derivative of L with respect to C, as this is the child of both tensors, and then it will just calculate this, but instead of A we are going to do it to B. So what you could say is that this can be seen as a function, and we will call this function grad fn. And grad of n will take as input the derivative of the loss with respect to the child. So in this case, it will contain the gradient of the loss with respect to C. So let's just write it like this, because once we know this gradient of the loss with respect to C, which is just this part of both equations, the only thing we then still need to calculate to know the derivative of the loss with respect to both these tensors is just this local part of the derivative. And yeah, this local part just depends on the shape of both tensors and on the operation that was used. So that will be exactly what this grad of n will basically contain. So we are going to construct a grad of n which will do this local derivative calculation and then is able to update both tensors. What this means is that every child tensor will be able to call a grad of n function in which it can input its own gradient. Let's just assume that this is already calculated, and then just use this to update the parent tensors by calculating a local derivative. And because we will later see this in C, this is done in C++, we can actually bind the values of the both parents inside this function. Yeah, we can just do this local derivative calculation. And what you should then know is that to calculate all these derivatives, we basically only need a small part of the graph at each point in time to do this gradient calculation. For example, we only need this part of the graph to calculate the derivative to A and B. We only need this part of the graph to calculate the derivative to C and D. And we only need this part of the graph to calculate the derivative to E and F. Because we can, let's just explain it a bit further. We can kickstart this entire process because we know that a derivative of an output with respect to itself, in this case the loss function, will just be 1. So we know that grad is 1, and we can then call the grad of n function in the L tensor with its own grad, which in this case will be 1. And using this grad of n, which will then contain the calculations for the, let me just, what am I doing? Grad of n1, okay, I was struggling a bit, but we can then call the grad of n function, which will contain the logic on how to calculate both these E and F. And then once we know actually E, we can let E invoke its grad of n function, which will calculate C and D, the gradients of that. Then we know C, and we can calculate A and B. So this is called the backwards pass, in which we are just calculating all these gradients and iterating to the graph in a backwards order. This might be a bit unclear, maybe think about it. I think it will also become more clear after the implementation. But as I said, what we are now going to do is basically calculate what this grad fn looks like, because it depends on if the tensors involved in the operation were a scalar, if it was a 1D tensor, if it was a 2D tensor, and also if the operation itself was an addition or a multiplication. So what we are now going to do is manually derive all these, you can call these local derivatives, for all these cases of operations and dimensions of input tensors. As I'm also getting a bit tired of drawing, let's just do some C++ quickly and implement everything we have learned so far and extend our tensor class. First, we are going to introduce a few new private variables, such as that we are going to keep track of the gradient for each weight we are storing with a grad variable, which will have the same size as data. It's important to notice that just like with data, we are storing this into a 1D vector, even though the tensor itself and also then the gradient might be a 2D tensor. So you should once again consider this gradient stored in row major order. If you don't know what that means, I would recommend you to watch the previous episode of the series. We also are going to keep track of a function which, as I said, will update the gradient of the parents based on the gradient of the child. So we are going to add this as a grad fn parameter, which takes as input a reference to the gradient vector of the child. And then, as you will see, we will use this to update the gradients of the parent. We will also keep references to the parents that created this tensor, as this will allow us to traverse the computation graph in a backwards order. We will also add a requires grad boolean to be consistent with PyTorch and to keep track of whether we actually want to calculate the gradient to this tensor. We are now going to extend the constructors a bit to also accept this requires grad variable, which by default is false, the grad fn function, which by default is null, and a by default empty parents vector, which is just like it is in PyTorch. We are now going to add a method to fetch whether the requires grad variable is true, a method to fetch the grad variable which is storing our gradients, a method to add a gradient update to our currently stored gradients, a method to initialize the gradients to a vector of the same size of the data we are storing, and a numel method, which, just like in PyTorch, tells us how many elements we are storing in our data. Also, in the constructors, we just assign the past values to the corresponding memory variables, and if we are required to track gradients, we just initialize the gradients to a vector of zeros with the same size as data, as we want to keep track of the gradient to each element in our data. Finally, I will also make the tensor class extend the enable shared from this, as this will allow a tensor to create shared pointers to itself. And we will need that to be able to pass a pointer to the tensor itself, to the children of the tensor. And let's now take a look at what this gradfn function looks like for all these cases. And if you would have told me 10 years ago that instead of playing the new Oblivion remaster, I would spend my time trying to teach people on YouTube how to calculate gradients, I would have probably thought that I had gone crazy, as I didn't even like mathematics in high school. But as you can see, you never know what you end up getting into in 10 years. Anyways, what we are going to check is basically this, the derivative of the loss with a specific weight for a specific function. And we are just going to go over all the different functions. Let's first calculate the scalar plus scalar case. And in this case, f, it just does a scalar plus scalar. So let's take a and b. And then the derivative of the loss with respect to derivative of a is just the derivative of the loss with respect to f times the derivative of this with respect to a, which is 1, and the derivative of the loss with respect to b is just the derivative of the loss with respect to f times the derivative of this of f with respect to b, which is once again 1. So in this case, the derivative is very simple, and we are just basically propagating the derivative of the child. In the scalar plus scalar case, the implementation is very simple. First, we are going to extend our implementation to check if either the tensor itself or the other tensor requires gradients to be tracked. And if that's the case, we are going to build a computation graph by creating a shared pointer to the tensor itself and store both this shared pointer as well as the shared pointer of the other tensor in a parents variable. We are then going to create the grad_n function, which is responsible for calculating and updating the gradients of the parents given a grad output variable, which represents the gradient of the child. In this case, we have seen that the gradient to both scalars will just be the gradient of the parent, and as this is also a scalar, the grad output will just have a single element, so we can just propagate that. So when this function will be executed later, the gradient of the parent will be added to the gradient variable of the self and other tensor. The only thing left to do is create a new tensor with the result as before, but now we also set the required grad to true and keep track of the grad_n and the parents. Maybe a bit more interesting is the case of adding a scalar to a one-dimensional tensor. So let's consider it like this. The one-dimensional tensor P2 Pn, and as we've seen in the previous video, how we should do this is just broadcast the A tensor to add to each element of the other tensor, A plus B2, and finally E plus Bn. But now, what is the derivative of the loss with respect to A? Well, obviously, it's a bit harder in this case because you should just realize that if you broadcast a tensor in the forward pass, in the backward pass, you should actually do a sum. So if you would have just taken this element and calculated the derivative to A, you would once again get a 1. And initially, when I was thinking about this, I thought that the derivative of f with respect to A would once again be like a bit of a tensor of ones, right? Because each local derivative here seems like a 1, but in neural networks, as eventually the tensor gets summed and reduced to a single loss value, what you should actually consider this is that you should sum all of these values, as A actually has, yeah, if you just think about how much A influences the output, it's through all of these dimensions. So you should basically sum all of them. And what this means is that this is equal to 1 times, and we once again also propagate the gradient of that of f on that specific position. So the gradient of the loss with respect to f on the first index plus 1 times the derivative of L with respect to the output on the second position up until the last. So the thing you should just remember is a broadcasting operation into forward pass is a sum into backwards pass. And now how are we going to calculate the derivative to b? Just like this is a bit more easy as the derivative of b is a 1D tensor with the same dimension of the gradient of the output tensor. So what we just need to do is derive this to b, which will once again first off be a tensor of ones, and then just multiply it with the gradient at the corresponding position of the loss with respect to f. And yeah, my drawing skills get a bit bad, but you should just what it boils down to is you are just passing the gradient of the child tensor, just basically the same gradient we are passing it along because we're just multiplying it with 1. In C++, we once again check if we are required to create a computation graph, store the parents. This time, as we have seen, the gradient to the scalar is just the sum of the gradients of the parents, and the gradient to other, which is a 1D tensor, is just the same as the grad output. Once again, we just return a tensor that tracks all of this. Okay, let's now look at scalar plus 2D. And this will be very similar to the previous case, as f is a plus this time a matrix, so b1 1 to b1 m or n, let's just take n, and this is element bm1 and the outer element is bm and the output, like I said, is in the previous video, you should just sum the scalar with all these elements. Okay, so now let's calculate the loss with respect to a, and once again we are broadcasting a. So what this is going to be is, this is once again the local derivative of each of these values to a, which is just going to be a 1 times the gradient of f on this specific index, and then we're just going to sum all these values. So yeah, it's just going to be a sum ij of just the gradient of L with respect to f on each of those positions. So it once again just takes a sum. And then for the loss with respect to b, this is once again going to be a 2D tensor. And once again, this contains a local derivative 1 on each position. So we are just going to propagate the gradient of the output. So on each of these positions, it will just consist of the derivative of the output. The implementation of the scalar plus 2D case is exactly the same as we are storing the gradients in a flattened vector. So we can once again iterate through all of that. And also for the 2D tensor, the gradient is just the parent gradient, as this is also a flattened 2D vector. Okay, let's consider some other cases, because we can also do 1D plus scalar. In this case, f is here the one-dimensional vector, a1 to an, and b is just a number. But this will be just the same as this one, except with a and b swapped, and the same for 2D plus scalar, where the f is a matrix, blah blah blah, and b is the scalar. This will just be the same as scalar plus 2D, but then with a and b swapped, so I will not repeat that. Okay, only two cases left, and that is 1D plus 1D, and let's also write down 2D plus 2D. Let's first do 1D times 1 plus 1D. F here is just a vector plus another one-dimensional tensor. They have to have the same dimensions, of course, and in the result we are just going to sum values at corresponding positions. So this also means that the derivative of the loss with respect to a will just be once again a gradient tensor with the same dimension of a, and as each local derivative, for example this, calculated derivative to a will once again be 1. So we are once again just propagating the gradient of the child tensor at each position. So this will just contain the derivative of the loss with respect to f at position 1 up to the last position, as the child gradient has the same dimensions as a and b, and this will be the same as the derivative of b. And actually the 2D times 2D plus 2D case is also very, very similar. We are once again going to define two tensors. And the result will be the elements at corresponding positions summed. And once again, you can see that the derivative of the loss with respect to a will just be the same as the derivative of the loss with respect to b, and that will just be a matrix in which we are once again just propagating the derivative of the child tensor on each position. In the 1D plus 1D case, the implementation is once again very simple. Just add the gradient of the parent to the gradient of self and other. The 2D plus 2D case is very straightforward once again. Just add the gradient of the parent. So in general, the gradients towards all these addition cases are very straightforward. And let's now look at some multiplications, as this will be slightly more complicated. So in the 1D times 1D case, what do we have right here? It's for example like this. We have a tensor A up to element n, and we are multiplying it with a tensor B up to element n. And this will result in a single scalar output, which we can construct by just multiplying elements at corresponding positions and then summing all of them. So it will be calculated like this. But what then is the derivative of L with respect to A? This will once again be a tensor of the same shape as A. And what we now need to do is for each element of this tensor, check how much this influences the output. So for example, A1, if we take the derivative of the output with respect to A1, it will be B1, the local derivative, and you also need to propagate the derivative of the output of the loss with respect to the output as before. So at this position, it will just become B1 times the derivative of the loss with respect to output, which is a single number. So we actually don't need to index into it. God damn it. So it will just be a single number, as the output is a scalar, so the gradient will also be a number. And then on the second position, it will just be B2 times this output derivative, and on the next it's Bn times the output derivative. Also, the other case, derivative with respect to B, will just, instead of that we are using B on every position, we will just be using A1 times the derivative of the loss with respect to the output, and then this for every on every position of our gradient tensor. So yeah, this case is also pretty straightforward. Now the implementation of the 1D times 1D case. Once again, create a variable to keep track of the parents. And as I explained, the gradient of self is each value of other multiplied with the output gradient. And the other gradient is the value of self at each position multiplied with the output gradient. Okay, let's now take a look at the 2D times 1D case, as this is once again a bit more interesting. So F will be the multiplication of a 2D tensor one n and we are going to multiply it with a single tensor. This should have the same amount of rows as the other tensor has columns, and the output will once again be a tensor, and on each position, for example, the first position, it's the first row times this tensor times B1 plus all kinds of additions. Maybe let's write one more out, times b2 until eventually we reach a1n times bn, and this is the same for each element of this output tensor. And then let's also calculate the last element, m1n in this case, times b1 plus am2 times b2 plus a mn times bn. So what does this mean for our derivatives? Because we are interested in derivatives. And the derivative of the loss with respect to a, once again, a 2D tensor. And we need to, for example, on the first position, see how much this element actually influences the output. And as we can see, the first element is used only here in the first row of the output. And the derivative, the local derivative to that is b1. So, because in the other terms, a11 isn't used. So it influences the output with a true b1. And we also propagate the output, the derivative of the loss with respect to the output of the first index in this first element. So what the derivative for this specific element is it's b1 times the derivative of L to F for the first element. And actually in the entire first row we are actually constructing this first element. So for this entire row we are just doing the derivative is just the element b for that specific index. So we just increase this, so this becomes b2 times dl df1, and just continue it like this. And at the end it will just be bn times derivative of the output with respect to n. I apologize for my drawing skills, but okay. And here on this, for this element, for example, we can see it gets used to construct this last element, and we are once again multiplying it with bn. So this will once again be bn, and the only thing that changes is that we are propagating the last element of the output gradients. So this means we have to index this in n-1, as this will lead to the last output. And for the rest it is just the same. This will once again be bn, and we take just the last element of the output gradient. So for the derivative to a is pretty straightforward like this. And also for the derivative of the loss with respect to b, this is a tensor. And now let's check how does, for example, this element influence the output. We can see that it gets used in this calculation, so it's multiplied with all the elements of this first column basically, because here it's used with this a11, and here it will be used with a21 until eventually a m1. So you can see this element influences the output on multiple positions. So we are once again going to sum. So maybe write a bit more like this. So we are once again going to sum, and we are going from in this case from 1 to m. So I is 1 to m to m, and what we are going to do is we are summing the AI1, and for each element we should also consider the output gradient, so we should also propagate the output gradients properly. And we can once again use I to index into this, I minus 1, because first we are using the first output gradient and the second output gradient, and for the last element, this corresponds to the last output gradients. So we are summing like this, and the last element, once again, we will have to construct it like this, but this time instead of using the first column, we are just going to use the end column. It might be a bit hard to follow this if you're just watching this video, but I would recommend you to manually derive it so that you can really get a feeling for it. The implementation of the gradient self will be a flattened 2D vector. So what we are going to do is iterate through self in row major order. The column index will determine by which element of the other tensor we will have to multiply the output gradient at the row index. We can then just push this result to gradient of self. The gradient of other is a 1D vector, so what we are going to do is iterate over all the elements of other with the index I, and then the gradient to the ith element is calculated by multiplying each element of the ith column of self with the output gradient, which is also indexed with the row index j. We then once again create instructions to update the gradients and return a tensor. Okay, now 1D times 2D. And I think I'm just, it's very similar to the 2D times 1D case. So for this one, if you want to derive it, I would recommend you to do it manually yourself. And as these math textbooks often say, proof is up to the reader or something like that. I'm kind of starting to understand why they do that, so let's move on. Okay, we have arrived at the 2D times 2D case, and this is probably the most complex one. So what's happening is we have a 2D vector or 2D tensor A, which goes from A1, 1 to A 1m, and we also have m rows, and the last element here is amn. What's now important is that the tensor which we are going to multiply it by also has n rows, so B11, this time up to Bn1, and let's also make it have m columns, B1m, Bnm. And the result, as I explained in the last video, we are just going to multiply the first row with each of these columns to get the first row in our result. Then we are going to multiply the second row with each column to get the second row of results. So let's calculate some of these by hand. So here what we are doing is first multiplying A11 times B11 plus A12 times B21 until we eventually reach the last element, and that will be A1n times Bn1. And so the first row times the first column leads to the first element right here. And this is going to continue until we multiply the first row times the last column. So this is A11 times B1m plus A12 times B2m plus eventually A1n times nm, right? Yeah. Okay, let's also calculate the other elements at the corners. For this element we are multiplying, so it becomes am1 times b11 plus am2 times b21. So, and we increase that until we eventually reach amn times bm1. And this element we are just multiplying the last row times the last column. So am1 times b1m plus am2 times b2m and then eventually we reach amn times nm. Wait, let me draw that a bit clearer. Okay, so this is basically what it comes down to, quite a calculation. And what we now need to know, of course, is what is the derivative of the loss, for example, with respect to A. This will be a tensor, once again, of the same size of A. So it once again be a 2D tensor. And first off, let's check for the first element, A11, how does it influence the output? And as we can see, that this element is used to calculate all the elements of the first row of the output tensor, and is always multiplied with a b11 up until b1m. So what we can say is that to calculate it on this position, what we are doing is first we need a sum which goes from 1 to m, and yeah, the local derivative to each of these elements will just be b1i, because once again it's influencing multiple elements of the output, so we need to sum them, and we need to also propagate the corresponding output gradients. And this will, what will the index of this be? This will be a 2D output gradient, And at each position, let's check. This will just be for the first element right here of A. This will appear only in the first row. So yeah, index it by 0. And we're basically iterating over the first row. So what we also need to do is iterate over the first row into creating the outputs, which we can do with using this I index -1 as it starts at 1. So that's it for this element. Let's calculate some others. Let's calculate the gradient, to this corner element, A1n. Where does A1n gets used? A1n, we can see it gets multiplied here with Bn1 and here with Bnm. So we are once again just going to define a sum which goes from 1 to m, and this time the way this element influences the output is through all these b and i's, and we once again multiply we propagate the gradient of the output, and this time it's once again the first row. So we index on row 0, and we will basically use the exact same index here because we once again just iterating over the first row. Okay, let's now calculate the gradient towards this element, AM1. AM1, you see we are using it here, we are using it on this position. So once again, we just need to sum from B11 up until B1m while also propagating the output gradients. So the formula will look like this. We once again go from 1 to m, and this time we are using once again saying that this is the b's always start with 1 and the index happens here, and this time we propagate the outputs of the last row, so m-1, and we are once again iterating over all the columns of that row, so we can use the index I for that. And now here the final element, I is 1. Let's see, AMN, where is it used? With these here with BN1 and here with BNM. So once again, just the same, we are going to sum over all these BN1s to BNM, and we are going to propagate the output gradients of the last row, which is m-1, and we are going to use the index to index into it. So this is basically the derivative with respect to A. So let's also do it towards B. So the derivative to B, this is once again going to become a matrix. Let's see, how is B11 used? We can see it's being used in the first column right here, and it's always multiplied with A11 up until AM1. So we once again just need to create an index, just need to sum over it. I mean, A from 1 to M. This time we are using A, and it ranges from I1 to IM, and we're also going to propagate the output gradients. This time we are propagating them by iterating over the first column instead of the first row. So now the column index is 0. And the row index is just the I minus 1. As we are iterating over it. Let's now do the corner elements. Once again, we already know we need some kind of summation from 1 to m. B1m, where is it used? B1m is here used in the last column. So we once again multiply it with a's from 1, 1 to m1. So we are indexing it like this. A1. And we are this time propagating the parents' gradients, or no, the child gradients, I mean, of the last column instead of the first. So just for completion, let's also do this one, Bn1, where is it used? Once again here and here. So what we are doing is we are going to multiply all these values, which range from a1n to amn. What was it again? Wait, I'm a bit confused. Bn1, okay, 1n. So it's all right. So it's these ones. And we are going to propagate the gradients once again of the first column. So we once again do this. Okay, finally, let's look at the last element. And that's this Bnm. Bnm is used here, and so we need to iterate over all these from a1n to amn, I, n, and it's once again the last row, last column we are iterating over, a1n. Okay, let's fix that a bit. So yeah, this is basically it for all our derivations. I'm getting a bit tired of writing it all out. In the 2D times 2D case, the gradients to self and other will once again be a flattened 2D vector. We are going to calculate the gradients in row major order, so this means that we first iterate over the rows and then over the columns. We are now going to calculate the gradient of the element on the ith row and the jth column of self. As we have seen, this comes down to multiplying each element of the jth row of the order tensor with each element multiplied by the ith row of the parent gradient. As grad output is a flattened 2D vector stored in row major order, we will have to index into it as follows. If you're new to row major indexing, I would recommend watching the previous episode to fully get this. Now for the gradient of the other tensor, we are going to do a very similar implementation. This time we iterate over the other tensor in row major order, and then for the element at position ij, we are going to compute the tensor by looping over the ith column of self and then multiplying each value with the jth column of the output tensor, summing it and then pushing it to the result tensor. We then add instructions to update the gradients of the tensor and create the computation graph the same as before. So the heavy lifting is done now, and we have implemented all the gradient calculations. In the forward pass, we are now going to build this computation graph, but once it's computed and we know the value of the loss, we will have to iterate in backwards order, starting from the child to the parents of that parent, and for each element for which we are tracking gradients, we will have to invoke the gradfn function, which will then calculate and update the gradients of the parents of the tensor. The way to kickstart the backward pass and compute all the gradients will be done by just calling a backward function, just like in PyTorch. Let's go through this implementation, as this will make everything a lot clearer. First, we will declare both a private and public backward method. We will also add a private variable to indicate whether a tensor has already been visited in the backwards pass. This is important such that if the same tensor is used twice in the computation, for example in a recurrent neural network, that we don't update the parent gradients twice. We will also add a reset graph visit method, which will be used to set the visited members of the entire graph to false. Let's start by implementing the public backward method. Just like in PyTorch, this can only be called on a scalar output that requires grad. We will first set all the elements of the entire graph to unvisited and manually set the grad to the current tensor to 1. This is because the gradient to a scalar is 1, and as this is the final output of their model, there is no child gradient to pass. We will then use this so-called private backward method, whose purpose it is to start from the final output and iterate over the entire computation graph in backwards order, calling the gradfn function at each step to update the gradients of the parent tensors. As at each step we have calculated the gradient of the tensor in which we are invoking the backward method, we can call the gradfn function to calculate and update the gradients of the parent tensors given the current gradient. So now our tensors are capable of building an entire computation graph in the forward pass of our neural network, and afterwards we can call this backward method to invoke a backward pass and calculate the gradients to each parameter of the tensors used in our graph. Let's quickly implement some tests to check if our implementation is correct. And indeed, everything is working as expected. Congratulations, we have now implemented a complete tensor class which is capable of being used to train neural networks. This is definitely the most challenging episode of this series, and I hope you understood everything. If you didn't, definitely leave some comments down below, as I want to explain it to you a bit more in depth maybe. But I personally found it very cool to implement all of this, and also know that we have this tensor building block. We can finally start by building some higher level components that make use of our tensor class and will allow us to finally define and train an actual neural network. If you're interested in finding out how we are going to do this, definitely consider subscribing. I hope you liked this video, and I also hope I see you in the next one.